In 1997, computer Deep Blue beat the highest rated player at chess. 2011, computer Watson beat champion players of Jeopardy! 2016, the game Go fell to the computer AlphaGo. But these are just games. What about a demonstration of practical problem solving? Enter AlphaGeometry, an AI developed by DeepMind that can solve Olympiad-level geometry problems, outperforming the average human participant. This has been heralded as a massive leap in AI reasoning and a step towards artificial general intelligence. But is it? I'll give my thoughts in this video. Firstly, how does it work? No coverage I've seen actually goes into any detail of AlphaGeometry's solutions. I went through them and it was so painful, I feel it's only right that I inflict that experience on others, but trust me, that pain is worth it, as it will help us in the second half of this video, where we discuss whether this is actually a step forward in reasoning and its potential impact on mathematics as a whole. First, a brief look at how AlphaGeometry works, and then a deep dive into one of the Olympiad problems it solved. It is made up of two systems, and I'll demonstrate what it might look like if it tries to prove this well-known result. The first system is a language model akin to a refined and specific use ChatGPT. I suggest ideas like plot the midpoint of this line, or draw this diameter. The second is a symbolic deduction engine. I know a bunch of geometrical theorems like m is the midpoint of AC, therefore AM equals CM. OA is a radius, this is a tangent, therefore this is a right angle, therefore this is 90 subtract x. These two systems work in tandem, with the first making a suggestion, let's draw these lines, and the second making deductions. Because M and O are midpoints, these lines are parallel, and they repeat until the problem is solved. Now let's draw this line. By Thales' theorem, this is 90. Angles in a triangle sum to 180, so this must be x. And by angles in the same segment, this is also x. Well done, guys. I don't always have the best ideas, but we usually get there. I'm always right, but my options are limited by this absolute moron who... Some commentators have likened this to a right brain generating ideas and a left brain analysing the facts. Let's see it in action with a more challenging problem. The International Mathematical Olympiad is one of the world's toughest mathematics papers for high school students, with each paper containing 6 problems selected from 4 mathematical domains. Let's focus on problem 1 of the 2008 paper, since AlphaGeometry solved this in 40 steps, which is fairly close to its average of around 55 steps. Before we state the problem, there might be some language with which you're unfamiliar. So here's a quick rundown of some triangle properties. Start with a triangle ABC, and first, it turns out that it can be embedded in a unique circle called the circumcircle, and its center is called the circumcenter. The center is the intersection of the perpendicular bisectors of the 3 edges, and I'll leave it as an exercise to justify why. Second, a line from a vertex meeting the opposite edge at a right angle is called an altitude. Every triangle has 3, and third, it turns out that all 3 altitudes meet at a common point called the orthocenter. Ortho meaning orthogonal, meaning perpendicular, meaning at right angles, you get the idea. Pause here if you need to just digest this. I'll summarize them here as I'll be using them for the rest of the video. The extended cut of this video goes into a bit more detail on these, like why the circumcircle and orthocenter even exist, and if you want to check that out as well as extended cuts of other videos, please consider supporting me on Patreon. So let's now look at this Olympiad problem. We'll start with some triangle ABC and plot its orthocenter H. Take the midpoints of the 3 edges and label them A0, B0, C0, so that A0 is opposite A, B0 is opposite B, C0 is opposite C. Now draw a circle centered at A0 which goes through H. Now this circle will cross BC twice. Call these points A1 and A2. Note these needn't actually be on the triangle. In an obtuse triangle they might drift outside, but we plot them anyway. Now draw circles centered at B0 and C0, each crossing H, and plot B1 and B2, C1 and C2 in the same fashion as A1 and A2. These problems really tend to front load a lot of information, so pause and digest this if you need to, because now, here's the question. We want to prove that A1, A2, B1, B2, C1 and C2 all lie on a circle. In GeoGebra, we can see that this seems to be true, but our task is to prove it. Pause now if you want to have a crack at it, then we'll look at AlphaGeometry's solution. So how did AlphaGeometry solve this problem? Well, first, it's worth noting that in the paper on AlphaGeometry, the problem is stated differently, just wanting to prove that B1, B2, C1, and C2 are cyclic. This is insufficient. By symmetry, a proof of this kind will generalize to the other pairs of sides, but it could be the case that the A's and B's, the A's and C's, and the B's and C's share different circles. But anyway, maybe they'll justify why this is sufficient later. Just a few things to mention up front. There are often a few redundant steps along the way. It often restates things already deduced. This is due to how it presents solutions, but I'll mostly just gloss over them and sometimes compress steps together. But I will show all steps on screen if you care about the minutiae. I'll assume a high school knowledge of geometry throughout. The results we'll need will be summarized here. One to draw your attention to is cyclic quadrilaterals. Most of us learn that opposite angles in a cyclic quadrilateral sum to 180, but the converse is also true. If you have a quadrilateral where opposite angles sum to 180, then it is cyclic. That's less obvious and it's going to be very important. I will be going through the steps fairly quickly. Now each step is fairly simple, but the length of the proof is quite overwhelming. My advice is not to worry about every little detail and just get a feel for AlphaGeometry's approach, but feel free to pause after every step if you want to fully grasp every detail. I'll use lowercase Greek letters for angles, and I'll use a star to denote a supplementary angle, i.e. alpha star is 180 subtract alpha. Let's get into it. We actually don't need these altitudes, so I'll hide them, and it starts by defining point O, such that EH equals EO. So clearly O must lie on this left circle, but also such that HO is perpendicular to EF. I think we can infer that O is actually where these circles intersect, but AlphaGeometry doesn't realize this yet. Step 1 is realizing that O must lie on the left-hand circle, so that's good. And step 2, it uses angles in the same segment to prove that these are the same. I'll call them alpha. Also, this is a cyclic quadrilateral, so these angles are supplementary. They sum to 180. I'll call them beta and beta star. Step 3, this triangle is isosceles, as EB2 and EH are both radii of this circle, so these angles are the same, and I'll call them gamma. Steps 4 and 5, here it infers that this angle is also gamma. Again, this is by angles in the same segment. Steps 6 to 8, it deduces that EF is parallel to BC by acknowledging that E and F are midpoints of those lines of the triangle. Steps 9 and 10 are some of the redundant steps I mentioned earlier, and step 11, we have that this is a right angle, and that's by Thales' theorem. Angles in a semicircle are 90 degrees. Step 12, AH is perpendicular to EF. That's because AH and BC are perpendicular by the definition of an altitude. BC and EF are parallel, so that angle must also be 90. Step 13. Now this one is interesting. We extend the line B2O to EF. I guess that's the right brain talking. We've run out of angles to chase, so let's just stick another line in. Now what's this angle here? Well, we have a right-angled triangle, so this is 90 subtract gamma, but here is another right-angled triangle, so this angle must be 90 subtract gamma. In other words, it's gamma. Steps 14 to 16 use this common right angle here to establish that AH is parallel to OH. The diagram is awkward here because it looks like this is necessarily the case, and it is, but AlphaGeometry didn't know that yet. Steps 17 and 18, this is a right angle, and again, that's by Thales' theorem. Steps 19 to 22 are more redundant restatements, and step 23, this is an isosceles triangle as EB2 and EO are radii, so these base angles are the same, and I'll call them delta. Steps 24 and 25, now this is a brilliant inference, and that's that this angle is also delta. All it says as justification is that these are delta and these are gamma, so why must this be delta? Well, here's a triangle with gamma and delta, so its third angle supplements them. But now here's a triangle with gamma and this angle, so its third angle must be delta as required. Step 26, again another fantastic inference, and that's that EF bisects this angle here. Now why is that? Well, call the top one epsilon, Yes, that's how many of us Brits pronounce it. And note this triangle up here, whose top angle is delta star. So epsilon supplements gamma and delta star. And now note this triangle, also with gamma and delta star, so this angle must be epsilon as well. It's great stuff. I mean, we can infer this so much more easily, but it is kind of cute how AlphaGeometry picks the most difficult ways to get there. Step 27, because F lies on the angle bisector of EO and EH, and because EO and EH are the same length, we have that FO and FH are also the same length. And step 28, therefore, O lies on this right-hand circle. Remember when we said as much at the very beginning? I told you we'd get there eventually. Okay, so it's putting a lot of pieces together, and step 29, what does it do with this newfound power? Well, what do you think? It's straight back to chasing the angles. So plot C2O and HC1. Now these are the same via angles in the same segment, and I'll call them zeta. Steps 30 and 31, these are clearly the same as they're both zeta star, and as a result, these angles are the same, I'll call them eta. And why is that? Well, consider this triangle and call its top angle theta. Then eta supplements theta and zeta star. Now consider this triangle, and we see that this angle also supplements theta and zeta star, so it must also be eta. Gonna need the whole Greek alphabet at this rate. Step 32, because these triangles have the same angles, they are similar, and that's expressed as this ratio. AH over AC1 equals AC2 over AO. Steps 33 and 34, this is quite fiddly, but we're doing a similar thing on the left as we did on the right with the zetas. So call this top angle kappa, and fill in this angle which we know is beta. We'll need it in just a second. This angle is 90 plus alpha, and we see that it is in a triangle with beta and kappa. But this angle is also in a triangle with beta and kappa, so it must also be 90 plus alpha. Step 35, similar to before, no pun intended, these two triangles have the same angles, so they are similar, and that's expressed as AH over AB1 equals AB2 over AO. Step 36, now a bit of algebra. We see that AH times AO is equal to AB1 times AB2 and AC1 times AC2. Therefore, AB1 over AC2 is equal to AC1 over AB2. Steps 37 and 38, we will use this ratio, so construct B2C1 and B1C2, and this ratio tells us that these triangles are similar, thus their angles are the same, in particular these ones, which I'll call lambda. Step 39, so close, this angle supplements lambda, so I'll call it lambda star. And step 40, finally, we have a quadrilateral B1, B2, C1, C2 with opposite supplementary angles. Thus, it is cyclic. Thus, these 4 points lie on a circle. Finally. So, what do we think about this proof? Well, for a start, it doesn't really answer the question. There is no demonstration that A1 and A2 must lie on this circle. Now this is easy to argue because consider any circle containing A1 and A2, then A1, A2 is a chord of the circle, and its perpendicular bisector must contain the center. But A1, A2 is a diameter of this circle centered at A0, therefore A0 lies on this perpendicular bisector. But recall that A0 is the midpoint of BC, thus this is actually the perpendicular bisector of BC. We conclude that any circle containing A1 and A2 must be centered on the perpendicular bisector of BC. Repeating the argument for the other sides, any circle containing all 6 points must be centered where all 3 of these perpendicular bisectors meet, which is the circumcenter. So all 3 circles must coincide. So AlphaGeometry successfully solves this problem, which isn't exactly the same as stated in the Olympiad paper, and I don't like how the writers have simplified the problem. Yes, it turns out that it is a solution in this case, but that requires justification and they haven't given any. The next thing to say about AlphaGeometry's proof is that it's quite meandering, to say the least. It isn't so much a solution, but more like watching someone else solve the problem in real time. When we're solving problems, we don't always have the best idea first, so we tinker and meddle and hope that our ideas go somewhere. What I'd love to see is that if later versions of AlphaGeometry can refine the solutions into something more palatable. For example, consider this. Step 1, define O as the second intersection of these circles. And step 2, EHFO is a kite, so its diagonals OH and EF are perpendicular. This is well known or provable in just a few steps, and if we can assume things like Thales' theorem, I think we can assume this. Step 3, E and F are midpoints, so EF is parallel to BC, and step 4, altitude AH is perpendicular to BC by definition, which means it's perpendicular to EF. Since OH and AH are both perpendicular to EF, they are parallel, and both pass through H, so in fact, A, O, and H are collinear. Steps 5 and 6 establish the betas as before, so these triangles with beta and kappa are similar, expressed as follows, and steps 7 and 8 establish the zetas as before, so these triangles with zeta star and theta are similar, expressed as follows. Steps 9 and 10 chase these ratios to establish similarity of these triangles as before. Step 11 establish the lambdas as before, and step 12 establish this quadrilateral as cyclic, and we're done. Now, I'm sure we could shorten this further, but without much thought, I took this from 40 steps to 12 with the benefit of hindsight. But my main issue with this proof is that the reason why the result is true doesn't leap out at me. A good proof should show why the result holds. The logic should enlighten us. And I don't find this particularly illuminating. However, this does veer close to my favorite solution to the problem. Consider the intersecting secant theorem. This says that if you have two non-parallel secant lines, one meeting the circle at A and B and the other at X and Y and crossing at P, then the following holds. AP times BP is equal to XP times YP. The converse is also true. If 5 points have this property, then those 4 points are necessarily cyclic. With that in mind, once we establish that A, O, and H are collinear, we have by the intersecting secant theorem that AB1 times AB2 is equal to AO times AH, and AC1 times AC2 is equal to AO times AH. Thus AB1 times AB2 equals AC1 times AC2, and by the converse of the intersecting secant theorem, these points are cyclic. This proof was written by a human, and there is a wealth of other succinct and creative proofs out there, but most importantly, this is a proof that to me finally does the job of telling me why the result is true. I can see it right in front of me, these seconds always combining at a vertex, and therefore giving rise to this specific circle in the middle. All who love mathematics love the spark of insight that proofs like this give us. We don't want to just learn the results, we want to experience the unique joy of resonating with this kind of logical poetry. It's beautiful. This isn't. But is that a problem? After all, it got the answer, and it did so in this unique way of combining creativity with deduction. So let's now take a broader look at what I think AlphaGeometry means for AI, and what it means for mathematics. Let me just remind you that I am not a computer scientist, I am a mathematician first and foremost. Everything that follows in this video is just like my opinion, man. Let me loop back to something I said at the start of the video, that previous AIs learned to play games while this one can solve problems. Well, is AlphaGeometry really solving problems? Because it looks like what it's doing is brute forcing its way around the angles and eventually landing on the result. But isn't that what problem solving is? AlphaGeometry's solutions are pretty haphazard and lacking in any general direction. Look at this solution for problem 3 of 2015's IMO. Horrendous. But if you try these problems, what do your initial attempts look like? I think for most of us, we just get our hands dirty and work out a bunch of lengths and angles before we have a good idea. We might have slightly more direction and intent behind our choices, but is our approach radically different to AlphaGeometry's? I don't think so, and I find this aspect of AlphaGeometry impressive and fascinating. A less impressive aspect of AlphaGeometry is that plane geometry is easy to codify in terms of strict rules and results. I mean, it's kind of telling that the oldest recorded axiomatic approach to mathematics is Euclid's Elements, and that begins with plane geometry. Olympiad problems are kinda like games. We know they have an answer. We know they are solvable with high school level results, because that's how they are designed. For the language model right brain, there are only certain things you can try and certain things that you need to try. Compare this to analytic number theory or algebraic geometry, where problems demand ideas that are way out there. This is to say that I don't think AlphaGeometry's achievements can be immediately generalized to other fields of study, no more than chess computer Deep Blue could attempt to play Go. For this reason that I respectfully disagree with some other commentators on this topic. Sabine Hossenfelder, for example, had this to say about AlphaGeometry.
It generally highlights AI's growing ability to reason logically, discover new knowledge, and verify solutions. And not only this, it can also explain how it arrived at a conclusion. Such a type of AI system has uses that extend beyond geometry. Not only can this achievement be generalized across various mathematical domains, but it'll without doubt also come in handy in other areas where rational thinking and logical deduction is of use. Like everything.
High school level plane geometry questions, which, remember, are written to be solvable, are comparatively easy, and there is currently no evidence to suggest that this technique can be generalized at this present time. Now, I'm not so naive to think that things will be different in the near future, especially given the rate of AI progress, so maybe soon an AI can tackle something like algebraic geometry, but not right now. A computer brute-forced chess, but it still took 20 years before a computer won at Go. Here, AlphaGeometry is answering geometry questions by, well, not quite brute force, but it's similar. And I think that we're still a while away from seeing AI have a go at some of the unsolved problems across mathematics. And come to think of it, given all the operations AlphaGeometry can do every second, it's still surprising to me that it still can't outperform the best humans. How weird would it have been if IBM announced that its computer Deep Blue attempted to beat Garry Kasparov but came second? No, the victory over the champion was the milestone. I'm not taking away from the achievements in this paper, I just think our excitement should be tempered a little. In my mind, this is a small step beyond beating games like Go, not a radical leap forward. It's natural then to ask about the future and whether AI will tackle unsolved problems. Those of you who have read the paper will know that AlphaGeometry developed many synthetic theorems, results proved from its foundation that help it make inferences. It even discovered a new result in this question, because its solution doesn't require one of the premises. I'd be gobsmacked if the question setters didn't already know about this and just added this constraint to tune the difficulty of the question. But is this a sign of AI eventually being used to solve open questions? And is that a good thing? Well, the first thing I foresee is AI-assisted proofs. These fall into a similar region of computer-assisted proofs, but there might be a difference. Computer assists are basically time savers. The four-color theorem, for example, required a lot of pen and paper research to break down the number of cases, each of which could then be checked by hand, but a computer can do it much faster, so it's more practical. Even simulations and data analyses essentially boil down to just doing a lot of calculations, which could be done by hand if we had infinite mathematicians writing on infinite blackboards, but we do it by computer to save time. A computer is just part of the equipment of the modern 21st century mathematician, along with chalk and blackboard. Along with traditional computer assists, AI assists might be considered part of our toolset as well, but AI might replace some of the creativity involved, and so would a purely generated AI proof. It feels like cheating, but is that a bad thing? Well, we need to ask, why do we bother solving hard problems? Other than to satiate our curiosity, I think there are three reasons. The first is that they have immediate practical value. These are things like optimization problems that could revolutionize aspects of computing, or cracking the Enigma code. It shortened the war. Direct impact. A non-mathematical example would be curing a disease. It's just good. The benefits are immediate and tangible. The second reason is that the theory or techniques we develop in order to solve them could be used elsewhere. This is the spin-off effect. Proving Fermat's last theorem, for example, required several leaps that connected many areas of mathematics and improved our overall understanding. A non-mathematical example might be that we didn't really gain any practical value from Armstrong setting foot on the moon, but many innovations were required to get him there which have everyday use. Thirdly, most importantly for me as a pure mathematician, and a reason I think is overlooked, it's just good to solve problems. You know, it's the old why climb Everest? Because it's there. Even without the innovations required for the Apollo missions, I still find the moon landing endlessly inspiring. Maybe the proof of the Collatz conjecture won't directly impact my life in the slightest, but I'll still find the event enormously inspiring nonetheless. Basically, the reason we solve problems, and really the reason we do anything, is either because it's useful or because it's beautiful. Or it's neither, like my PhD thesis, but still, both reasons are valuable. So here's my take on AI in mathematics. If a solution to a problem has immediate practical value, we should use AI and cheat and get the answer. Who cares if we look up the answer to a disease cure? It'll save lives. The second case gets a bit weird though. I worry that AI-assisted proofs might not develop interesting spin-off theory and instead force the solution out of pre-existing knowledge. When humans puzzle for a long time, they force themselves to be creative, and that's where the new theory lies. AI might get the answer with a messy and haphazard application of more basic stuff, so we miss out on potential new techniques. This isn't exactly the same, but by analogy, it's like this geometry problem. Did you know the intersecting second theorem before you saw this proof? You might have done, but AlphaGeometry on the other hand applied the same few results over and over. Admittedly, that's just my opinion, I don't really have any direct evidence of this, but we are already starting to see stagnation in other areas of AI-generated content. But my main reservation with AI-generated proofs is this third point, the beauty. I know AlphaGeometry wasn't designed to create beautiful proofs, and again, this is just my opinion, but I want to convince you why beauty really matters. Imagine if an artist composed the greatest painting ever. There is likely no practical value to be found in the painting, or in any of the techniques developed to compose it, but we wouldn't say that it's pointless. As an enormous cultural contribution, it would still enrich our lives in ways beyond what is practical. Well, mathematics is part of our culture. Has your life tangibly and practically improved because Wiles proved Fermat's last theorem? Probably not, but the story likely inspired you. The result was as much an enriching cultural contribution as a great piece of art. Would the story have inspired you if an AI had proved Fermat's last theorem? And this is again where I disagree with Sabine. I know this last comment was a bit of a joke, but rational thinking and logical deduction aren't useful for everything. I can't rationally convince you why this proof is beautiful. To me it just is, and nor can I convince you why AlphaGeometry's proofs are ugly. And does this matter? Yes, because we're in the land of plane geometry, which isn't some untapped wilderness of mathematical usefulness, it's a playground, squarely in the domain of beauty. And what makes something beautiful? I don't know, it isn't the length of the proof, as shorter isn't always better, and it isn't simplicity, as too simple often hides or disguises the inner workings. We just know it when we see it, and I don't think AI has come close to capturing beauty yet. There's a line about aesthetics in the AlphaGeometry paper, how AlphaGeometry might discover some plane geometry results overlooked by us humans because it isn't biased towards symmetry or that which is aesthetically pleasing. And great, you do you, AlphaGeometry, but if it isn't aesthetically pleasing, why do we care? Mathematics is often seen as something that's purely logical, it's black and white, and we love it for that. But we also love it for the aesthetics. Like, be honest, if I made a video saying, here's an ugly geometrical result, and here are the 100 difficult steps it takes to get there, would you care about that? No, I curate topics that expose mathematical beauty. Even when the solution is kind of ugly, I try to make every step intuitive so we can appreciate the symmetry, the hidden magic, and the beauty within. 3 Blue 1 Brown's video on collisions printing pi. It's a jaw-dropping result. But we all watch the whole video because the real awe comes not from seeing the answer, but from seeing why. That's what we love. That's what inspires us, not this. I want to be super clear here, I am not criticizing AlphaGeometry or the authors of this paper. AlphaGeometry wasn't designed to create beautiful mathematics. It was designed to solve Olympiad problems, and it does that pretty well. All I'm saying is that while AI might be close to solving problems, I think it's far from solving problems beautifully. This is where my concerns lie and why I'm not yet excited about AI-generated proofs. To me, mathematics is the most creative and beautiful thing there is. My qualms echo those who love visual art, music, and film, and fear that artists, musicians, writers, and actors will be replaced by AI. This replacement will be a cultural net negative. If AI also solves our mathematical problems, we might sacrifice their cultural impact as well. Thank you so much for watching. Bit of a different video this time because I wanted to respond to the news. I think AlphaGeometry is a fascinating new approach, but the more I thought about it, the more I felt I needed to say. So I hope you enjoyed, and if you disagree with my take, that's absolutely fine. Let me know down in the comments and keep the discussion respectful. A massive thank you to all my patrons who keep the channel alive. If you'd like to support me, you'll get your name in the credits, access to extended cuts of select videos, we get to hang out on our dedicated Discord community, and more. If not, don't worry, subscribe and share the video, that will help me out as well. This has been a human-made proof under another roof. Until next time.